Hey Team Pecan, and welcome to today's lecture, where today we're going to talk about thermal energy and the Boltzmann distribution. So some recap from our last lecture where we were talking about electronic spectroscopy. Some of the key things that we learned is, first of all, that electronic transitions, just like vibrations, just like rotations, obey selection rules. Those selection rules depend on whether we're talking about an atom versus a molecule, but all electronic transitions have the selection rule delta S equals 0, meaning that the spin state of the molecule can't change as we go from ground to excited state. Something else we learned is the Frank-Condon principle, which taught us what types of transitions are most likely to occur going from ground to electronic excited state. And in that case, we learned that the electronic transitions are vertical. So there's no change in the nuclear coordinates as we go from ground to excited state because the electrons in a molecule can move much faster than the nuclei of the molecules. And also, electronic transitions are most likely to occur between vibrational states whose wave functions have significant spatial overlap, quantitatively, which we can compute using Frank-Condon factors. The third major topic that we learned about last time is that a molecule, in order to go to the electronic excited state, has to absorb a photon of light. But from there, there's one of several pathways that the molecule can take to get back to the ground state. Two important examples are, first, that the molecule could undergo a vibrational relaxation to get to the ground vibrational state of the electronic excited state, after which the molecule can undergo fluorescence, a radiative process where a photon of light is emitted to get us back to the electronic ground state. Or an alternate pathway is that the molecule goes from a singlet excited state, S1 on the diagram I'm showing on the slide, via an intercessor crossing to a triplet state, T1. Once again, once it's in that triplet state, the molecule will undergo a bit of vibrational relaxation, and then eventually, over a very long time, because it's a forbidden transition according to our selection rules, finally the molecule will be able to emit a photon of light. And that process is known as phosphorescence. And we didn't have a lot of time to discuss it in class, but I do want to emphasize that so many different types of spectroscopy and imaging rely on these twin techniques of phosphorescence and fluorescence. And so whether you're thinking about biological imaging or doing single molecule experiments, these types of spectroscopies are really interesting. And one example that we have seen already in this course is quantum dots. We discussed quantum dots and their fluorescent properties in the context of making quantum dot TVs, but you also got to read a little bit about how they can be used in making solar panels and in medical imaging. So there's really a lot of application areas for electronic spectroscopy. To summarize a little bit more broadly what we've been doing over this section of the course, we've been honing in on how molecular motion and different types of motion can give rise to different energy components of a molecule's internal energy. We learned that molecular motion can be grouped into 4 distinct categories: translational motion, rotational, vibrational, and electronic. And one thing that's really important is that focusing on the individual types of motion, quantum mechanics and solving the time-independent Schrodinger equation can tell us what the expected energy level diagram should look like for each type of molecular motion. It's from quantum mechanics that we obtain formulas for the energy levels themselves. And so to give a concrete example, when we talked about vibrational motion, we solved for the harmonic oscillator model in order to determine that the general energy expression for these energy levels is E sub nu equals nu, our quantum number, plus a half, times Planck's constant times the square root of the bond force constant K divided by the reduced mass mu. And so into this formula, if we plug in nu equals 0, that will tell us what energy is the vibrational energy level. And I've highlighted that energy level and what that corresponds to in green on the right-hand figure. Similarly, if we plug in nu equals 1, that'll tell us what the energy is for the nu equals 1 state. And so quantum mechanics really deals with giving us these absolute energies. Spectroscopy, in a complementary but somewhat distinct way, is mostly important because it helps us measure the energy transitions associated with moving between levels. And so in spectroscopy, we're not measuring these green absolute energies, but instead we're measuring energy differences. And so for vibrational spectroscopy, in order to understand where on the x-axis these different peaks are showing up, say in an IR spectrum, we have to compute this energy difference, and that will tell us what it is that will help us relate our quantum mechanical predictions to our spectroscopic experimental outcomes. Something that was kind of hinted at in the section of the course, but that I want to make explicit before we move on to today's topic, is that just as with the orbital approximation, if our one electron wave functions operate independently, the overall wave function ends up being a product, and the overall energy ends up being a sum of the individual components. The same thing happens with our 4 different types of molecular motion. And so if we can approximate the motions of translation, rotation, vibration, and electronic motion as operating independently from one another, then the molecule's wave function is a product of the individual terms, and its energy is a sum. This is a pretty good approximation for understanding molecular motion, although if you went into advanced research, there'd be a couple opportunities for us to question some of this independent motion assumptions. However, for our purposes, this is how I want you to think about molecular wave functions and molecular energies. Energy is just a sum of the different contributions from the different types of motion. Now, to introduce a little bit of terminology that we're going to use throughout the rest of today, we want to be able to identify the state of a molecule unambiguously. And so long as we specify for a particular molecule at a particular moment, what are its quantum numbers? Electronic quantum numbers has 4 of those. Rotational quantum numbers has J and M sub J as its quantum numbers. Vibrational motion, we saw had a quantum number of nu, and translational quantum numbers, we saw that there was 3 different translational quantum numbers associated with the 3 different types of motion, which we got from our particle in a box model. And if we specify all of those quantum numbers, that defines very specifically what the energy of that molecule should be and what its state is going to be. And the term that we use to describe this exact specification is a microstate. So for today's lecture, we're going to revisit some of the questions and assumptions that we made throughout the spectroscopy unit. I hope that in particular there was a couple of statements that were made earlier on in our lecture series that were given to you as sort of axioms where you just had to trust me that they were true, but that there wasn't any motivation or logic given for. Some of the statements that bugged me the most during my spectroscopy unit when I was first learning this material was some of the following. I was told, but had no idea why I should expect that all atoms or molecules, I'm going to start calling them particles so that I don't have to say atoms/molecules all the time, but that all particles are in their electronic ground state. Don't you dare at room temperature assume that something would be in an electronic excited state. I've also said that for vibrational spectroscopy, most particles are in their ground vibrational state. And, well, there's a small fraction of particles that might be the excited state, and we'll just have to say to approximation, we'll treat most of them as in the ground state. Suddenly when we got to rotational spectroscopy, we flipped gears. And I said, oh yeah, rotationally excited states are totally a thing at room temperature. In fact, very few particles are found in the rotational ground state. And as a concrete example, with carbon monoxide, J equals 7 is the most probable state for a molecule to be in at room temperature. And then further on from that, we said that particles exist in a wide variety of translational states, and typically to the point where we actually consider the translational energies classically, kind of like what we did way back in homework 3 when we were discussing how nitrogen might move around in a box. And we discussed it as a continuum rather than a discrete set of energy levels. And we assumed that at room temperature, that nitrogen molecule is going to be at a very high quantum level, or have very high translational quantum numbers. And the question is why? What is it that makes rotational energy levels so different than electronic energy levels? And why is it that they behave so differently? So to unpack this mystery a little bit, we're going to go about this using a little bit of our chemical intuition, a little bit of our prior GChem knowledge, and then a little bit of some formalisms that Maxwell and Boltzmann came up with back in the day. So here's my thought experiment. Let's consider a hypothetical system where I have a particle and it can exist in one of two microstates. So again, that word microstate means that psi1 corresponds to a set of electronic, rotational, translational, and vibrational quantum numbers. We're just going to call it psi sub 1 to say this is one unique microstate. And similarly, we'll have psi 2 corresponding to a different microstate. They happen to have the same energy in this case, so they're degenerate, but they have unique, or at least slightly different sets of quantum numbers, such that they're different microstates. So here is I'm going to use a circle to represent my particle. So here is my particle being found in the psi 1 state, or I could also find my particle in the psi 2 state. And so I'm going to announce a thought experiment question for you and then give you a moment to pause the video and think about this for a little bit. Which of the following statements correctly represents, do you think, again, based on your prior background knowledge coming into this course and or just your gut intuition, which statement should correctly represent the probability of observing the particle in microstate 1? Should it be equal to the probability of observing it in microstate 2? Bigger probability, smaller probability? Take a moment to pause the video and try and answer this question yourself. So it turns out that, and again, just using our intuition, there's nothing different energetically about psi 1 versus psi 2. And since what matters most to a chemical system is its energy, it stands to reason that there would be an equal probability of observing the particle in either microstate. In fact, because this is a statement that is so based on intuition, it's treated as a postulate. And Boltzmann's equal probability postulate is that all microstates with the same energy should have the same probability of being occupied. Kind of makes sense. But what if the microstates have different energies? Let's now consider a hypothetical system that has a large number of particles, and each particle could exist in one of the 3 different microstates. So it could be in psi 1 as a microstate, could be a little bit higher up in energy in psi 2, or could be up in this psi 3 state. I'm going to ask you the same question to pause the video and see if you can use your intuition or your prior background knowledge to come up with a hypothesis as to what the right answer might be in this case. Now it turns out this problem actually we need a little bit more information before we can address this, because I've drawn the relative energies of psi 1, psi 2, and psi 3, but I haven't distinguished if these are big gaps or small gaps on this energy scale, or how the size of the gap should influence the probability. To understand that, we're going to have to talk a little bit about kinetic energy and what thermal energy means on a microscopic level. So thermal energy is a topic that we discussed a little bit in GChem, a little bit in your first PChem course, but to think about energy in terms of physical constants that you may be used to, we're going to utilize an important result from the field of statistical thermodynamics. And this theorem is called the equipartition theorem. It states that in thermal equilibrium, particles have an average kinetic energy of 3/2 kBt, where kB is Boltzmann's constant, it's just a number, and T is the temperature of the system in Kelvin. Kinetic energy is termed thermal energy because kinetic energy depends very directly on what the temperature of the system is. And so even though the equipartition theorem tells us the average thermal energy of each particle, 3/2 kBt, to really understand what the probability is of us occupying different states with different energies, we have to think a little bit about what the distribution of kinetic energy for a system is. How much thermal energy do individual particles tend to have? And that distribution is something that you've actually seen before in general chemistry, the Maxwell-Boltzmann distribution. So as a recap from your GChem, the Maxwell-Boltzmann distribution is a probability distribution. So kind of like what we saw for the wave function, again, very different topic, but the math behind it is the same. When we see these different curves corresponding to different temperatures, it tells us how many particles we expect to have a certain amount of kinetic energy. And you may remember from GChem that in this case, this blue curve, where most of my particles, the average kinetic energy is quite a bit smaller, that blue curve is going to correspond to lower temperatures of the system. And as we go to higher temperatures, the average kinetic energy moves to the right. Particles gain more and more kinetic energy at high temperatures. And also you notice that the distribution kind of starts to broaden out a little bit. And so how does this relate to microstate populations? Well, to reach an excited state via thermal energy, so now we're talking about non-radiative processes as opposed to trying to excite a molecule into a new state using light. To get from, say, Psi1 to the Psi2 or the Psi3 state using the molecule's kinetic energy, a particle, well, needs to have enough kinetic energy that is greater than or equal to the energy difference between the two microstates. Only then does it have enough kinetic energy to take that kinetic energy and turn it into potential energy to move up in terms of its energy level. And so I've taken this yellow arrow, which on my diagram to the left is shown energy is on my y-axis, so it's a vertical arrow. To relate this to the Maxwell-Boltzmann distribution, I need to rotate this arrow 90 degrees because in this Maxwell-Boltzmann distribution, my discussion of energy is occurring on the x-axis. And I want you to notice something really interesting. Based on this Maxwell-Boltzmann distribution, only particles to the right that have greater kinetic energy than where this line is have enough thermal energy to undergo a transition to the excited state. And so let's focus initially on a set of particles that are at temperature T1. Again, that's our cold temperature. Notice that it's a really small fraction of our particles that have enough thermal energy to be excited up all the way to Psi3. And so how we would phrase this as chemists is that because the energy difference between Psi3 and Psi1 is large relative to kBt1, that's the Boltzmann constant times the amount of thermal energy, thermal excitations are unlikely. On the other hand, if we're considering T3, that's going to be like a hot temperature, that red curve, in this case, it appears that well over half of the particles have enough thermal energy to be excited up to microstate 3. And so in this case, we would say that the difference between energy levels is small relative to kBt3. And so thermal excitations should expected to be pretty common. So using this information about how, when we're considering energy scales, we always want to consider the energy differences between levels relative to the available thermal energy of the system, 3/2 kBt being a pretty good proxy for how much thermal energy we expect a particle to have on average. Let's revisit our original question about microstates. And for the purposes of this discussion, I'm going to say that our thermal energy available to the system is given by the size of this yellow arrow. So go ahead and pause the question and see if you can understand which of the following statements correctly represents the probability of observing a particle in microstate 1 relative to microstate 2 or microstate 3. So in this case, the answer to the question is B. Because the energy difference between psi 1 and psi 2 is small relative to the available thermal energy, it should be very common to see the particle either in state 1 or in state 2, with the probability of observing the particle in state 2 just a little bit smaller than that of observing it in state 1. On the other hand, the average thermal energy of the system makes it very unlikely for us to visit state 3 if we're starting in state 1, because 99% of the molecules are just not going to have enough energy to be able to make that jump. What, though, happens if the kinetic energy changes? And let's do a thought experiment where the average kinetic energy per particle is so large as to be nearly infinite. How does that if at all, change what statement correctly represents the probability of observing the particle in microstate 1 in this case? Pause the video and see if you can think this one through. So it turns out that in this case, if in the limit that the kinetic energy is so large compared to the differences between my different states, to pretty good approximation, we can say that that difference is negligible. And we kind of resort back to our original thought experiment, where all the states are, roughly the same in energy. And so we have equal probabilities of observing the particle in any one of these 3 microstates. And this kind of goes back to our original discussion of formal versus accidental degeneracies. For this situation, when the 2 states are relative to the amount of thermal energy practically equivalent, we say the states are accidentally degenerate. And we expect to see all 3 of these states populated with equal probability. So hopefully this thought experiment was helpful for us to understand some of the principles behind how kinetic energy and the available thermal energy in the system might influence whether or not we expect to naturally visit excited states, even without needing light to occur that absorption transition. But let's make things a little bit quantitative now. Boltzmann was able to derive a formula that exactly yields the relative probabilities of observing the molecule in 2 different energy levels. I'm not going to, for the purposes of today, go through the derivation of how he got to this point. However, if you're really interested, you can check out your Atkins textbook. What's important for our purposes is that the Boltzmann distribution equation tells us how frequently we view a particle in a state energy level I versus energy level J. And it turns out to depend on a couple of different factors. So in this equation, capital N is the number of molecules that we expect to observe in a certain state. In this case, the ith energy level. And since we're talking, really we want to talk in terms of relative probabilities, that's why we're talking about Ni divided by Nj. So what's the ratio or the relative probability of viewing the particle in, say, a ground state I versus an excited state J? And the factors that this ends up depending on is, first of all, in a way that hopefully feels intuitive to us, it depends on the difference between the I and J energy levels themselves. And that shows up in a decaying exponential. So you can see that if the ratio of the difference in energy levels versus KBT, if that energy difference is negligible, the exponent is pretty close to 0, and that means that, the energy levels are the difference is pretty negligible relative to KT, versus a case in which my energy difference is really large compared to KBT. Now that exponential is going to be much smaller than 1, and that's really going to influence what is able to be observed between these 2 different the number of particles available to the different states. The other factor that it depends on is the degeneracies of the I and J of energy level. So rotational spectroscopy is a really good example of this, where our degeneracies were equal to 2J plus 1. So as we went to excited states, there's just more and more options available for the particle to go to. And part of the Boltzmann distribution equation says that the more states there are at a particular energy level, the more probable it is to find molecules in them. And so that's why the degeneracy comes into play in this equation. And last but not least, again, Kb is Boltzmann's constant, T is the temperature in Kelvin. So now that we have this equation, let's practice using it. And so let's consider a typical molecule at room temperature. What would we expect to be the approximate ratio of molecules in the ground vibrational state versus the first excited state? And as a reminder, our harmonic oscillator model tells us that each of the vibrational levels should be singly degenerate. So in this case, both Gi and Gj are going to be equal to 1. Go ahead and pause the video for a couple minutes. I've given you some options to make this a multiple choice question, but go ahead and pause the video and see if you can figure out for yourself what the appropriate ratio should be. And when we come back, we'll go through it together. Okay, so for our purposes, G0 and G1, like I said before, are both going to be 1. And since we're talking about the ratio of the ground state to the first excited state, I'm going to calculate N0 divided by N1. So substituting in I equals 0 and J equals 1, the energy difference that I need to calculate is the difference between the nu equals 0 and the nu equals 1 state. If we look at remind ourselves of our typical energy gaps between successive energy levels, remember that for vibrational energies, it's something on the order of 10 to the negative 20th joules. And since we're talking about E0, a lower energy, versus E1, a higher energy, that's why we need to plug in, inside of my parentheses, negative 10 to the negative 20th joules. Divide that by Boltzmann's constant and the temperature for room temperature. And when we plug that into our calculators or our Excel spreadsheets, we get that that ratio is 19.1. What that means is that for every 19 molecules in the ground state, there exists 1 molecule in the first excited state. And hopefully this quantifies a little bit some of the assumptions that I just gave us as axioms when we were talking about vibrational spectroscopy. The reason that we say that the fundamental transition between 0 to 1 is the most important and usually only observed transition in IR spectroscopy is that 19 times out of 20, a molecule is going to be in the ground state rather than the excited state. And we only observe transitions related to what initial states we find our molecule in. And so while it's not a perfect approximation to say that all molecules start off in their vibrational ground state, it's a pretty good approximation. And it's only if we are able to have really high resolution, high signal to noise spectroscopy that we may start to be able to observe some tiny peaks, low intensity because it's low probability, of that nu equals 1 to nu equals 2 transition. Starting in the nu equals 2 state, nu equals 2 to nu equals 3 transition, that's going to be far less likely, simply because of what the Boltzmann distribution equation tells us in terms of what room temperature spectroscopy would look like. And one thing that's really fun to note is that temperature gives us a little bit of a handle on how to make certain peaks in the vibrational spectrum show up more prominently or less prominently. So if we really wanted in our spectrum to exclude the nu equals 1 to nu equals 2 transition, we could run our IR spectrum at lower temperature, and that would make it even less likely for us to observe that nu equals 1 to nu equals 2 transition. On the other hand, if that's something that we were interested in, running our IR spectrum at higher temperature would allow the molecules to be thermally excited into that nu equals 1 state, meaning that we could observe via light that nu equals 1 to nu equals 2 transition. Pretty neat. Okay, let's do a second example. So for a typical molecule now at room temperature where we're considering rotational spectroscopy, what should be the ratio of molecules in, say, the ground state rotationally to the 7th excited state? And as a summary or a reminder from our previous lectures, remember that the degeneracy of the jth level in rotationals, our rotational energy levels, is given by 2j plus 1. And also remember that the energy level, those absolute energies for our rotational spectroscopy, is equal to j times j plus 1 times a group of constants that are roughly equal to 10 to the negative 23rd joules when you plug in all of them together for a typical molecule. So see if you can use this Boltzmann distribution equation to figure out what the ratio is of molecules in the ground state to those in the 7th excited state. Pause the video, and when you come back, we'll go through the problem together. Okay, so we're going to use the same formula as we did before, and one difference is that here we have to remember to plug in the appropriate degeneracies. So the degeneracy in the 0th state is 1, and the degeneracy in the 7th state is 2j plus 1, or 15. Using our formula for what E0 versus E7 should be, we get, once again, a negative number since E0 is a lower energy state than E7, but in this case we get something on the order of negative 2.15 times 10 to the negative 21 joules. And when we plug that into our Excel spreadsheet, we see that the ratio is equal to 0.13, or in other words, that means that for every 1 molecule in the ground state, there's going to exist 8 in the 7th excited state. And so for this reason, we assume that molecules exist in a wide distribution of rotationally excited states. And what's really interesting to note here is that it explains for the first time why it is that in vibrational spectroscopy we only see 1 peak, versus in rotational spectroscopy we see a lot of peaks. And the reason comes down to 2 different factors. In vibrational spectroscopy, the energy levels are pretty far apart relative to the available thermal energy. And they're all singly degenerate, meaning that we don't get any benefit to going into the excited states because we don't have any more options than we did in the ground state. With rotational spectroscopy, on the other hand, first off, the gaps between energy levels are much smaller. It's much more likely for us to be able to visit those using our available thermal energy. Furthermore, as we go up in energy levels, there exist more and more available states. And so that degeneracy factor makes it suddenly not only somewhat likely to visit the rotationally excited states, but in fact more likely to be in a rotationally excited state versus the rotational ground state. And when I suddenly made this connection between the Boltzmann equation and how that led to the population of the peaks in my rotational spectroscopy, it was a real light bulb moment for me, because it's only through understanding thermal energy that we can understand why we would get this multitude of peaks in our rotational spectrum. And in fact, one thing that you can do is you can calculate sort of what's called the Boltzmann factor, the degeneracy times e to the negative e sub j divided by kt, and show that depending on the temperature, there'll be a certain highest, most probably populated energy level. And at room temperature, for a molecule like carbon monoxide, that highest, most populated value is at the J equals 7 level. And so around this temperature, that's the transition that's going to be the most intense in our rotational peak. And so it explains, if you look at the chart, why we sort of see a rise in peaks where it becomes more intense, more probable to see a certain transition, again, because we have more molecules in that particular initial state. And then over time, as we go higher in J, eventually this dies off because the energy gap gets too big, or the energy higher excited rotational states become too high in energy for us to be able to thermally visit. If we change the temperature of the system, we can allow the system, the particle, to exist in more excited states, and that in turn leads to a broadening of our rotational spectrum. And so it's now we can see, using the Boltzmann distribution, why it should be that carbon monoxide would have such a strong temperature dependence in terms of how its rotational spectrum looks and how many peaks we expect to show up. And hopefully now you can kind of appreciate why. All right, so that's all I've got for us for today's lecture. There's a couple of takeaways that I want us to see, but really one takeaway for today. We had a bunch of mysteries coming into this point in the course to understand why it is that for electronic spectrum, all molecules and atoms should be in the electronic ground state, but for rotational spectrum, we see particles more frequently than not in a rotationally excited state. And the relative occupations of different microstates turns out can all be explained by the Boltzmann distribution. In my experience, this is one of the most important equations in chemistry to understand because it helps us understand not just what one molecule might be doing, but how a distribution of molecules might behave, not only in terms of their kinetic energy, but also in terms of how much potential energy they might have. And that has implications for spectroscopy, for dynamics, and for a wide variety of chemical phenomena. So once we get into class, we're going to have some practice problems to help make these concepts stick a little bit more. But until then, I look forward to seeing you all in class. Take care, folks.